We have finally made it to chapter 2. We have spent a good bit of our time talking about limits, and for the most part, for now, limits are behind us. But we will see here in just a second why we even had to have this discussion on limits, um, so that we can understand what the derivative is and how we find it. And that's what we're going to look at first. Now, we want to talk about, in this chapter, of course, we're going to be talking about differentiation. We'll find out what that is. And we're going to be looking at, in this section, the derivatives and the tangent line problem. Okay, so we'll start with the definition of tangent line with a slope of m. If f is defined on an open interval c, and if the limit as delta x approaches 0 of delta y over delta x equals the limit as delta x approaches 0 of f of c plus x minus f of c all over delta x equals m exist, then the line passing through c f of c with slope m is the tangent line to the graph of f at the point c f of c. Okay, so that says a lot. But basically, we are talking about a line that estimates the slope at a particular point. And we'll look more at why this formula is what it is. But let's just talk about a couple of things here. Of course, we've seen delta x before, and we said that represents the change in x values. Delta y would be the change in y values. So we got the change in y over the change in x. That should sound familiar because that's pretty much what our slope formula is for a linear function or a line. We looked at the change in y over the change in x. However, now we're applying this limit process because we don't have just a consistent slope. We need to look at that slope by taking points that are successively closer and closer and closer to c. That's why we're using this limit process, because we're doing that closer and closer thing that we learned about in chapter 1. But after we have done that, then we want to keep in mind this definition. Okay, you want to definitely store this in your memory bank when we talk about the definition of the tangent line and the slope of that line. It's going to be the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. And again, this is just the change in our y values over the change in x. Okay, so let's take a look at how we can apply that. Okay, we want to find the slope of the tangent line to the graph of the function at the given point. And we'll do it first for g of x equals 3/2 x plus 1. So we're going to write our definition first. Okay, it said that m was equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, so for us, we don't have f, we actually have g, but we'll go on with this notation. We're still looking at the limit as delta x approaches 0. Okay, if I plug x plus delta x into this function, I get 3/2 x plus delta x plus 1, okay, minus 3/2 x plus 1 all over delta x. Okay, so let's take a look at this for just a second, just to make sure we're clear about where our pieces are. We have f of x plus delta x, and that's what we have here. Okay, we were able to evaluate that by using the function and plugging in where we had x plus delta x. Even though we don't have an x here on this 1, it's still a part of the function, so it's there. Okay, then we also have just f of x. Okay, and so that's this piece. Okay, f of x or g of x was 3/2 x plus 1. And then we're dividing by delta x. Now we're ready to simplify. So we still have the limit as delta x approaches 0 of 3/2 x plus 3/2 delta x plus 1 minus 3/2 x minus 1 all over delta x. Of course, we were careful and we distributed the minus sign to each term that followed in parentheses. Okay, looking at this and simplifying, we see 3/2 x is going to cancel out. We got a plus 1 and a minus 1. That cancels out. So we're left with the limit as delta x approaches 0 of 3/2 delta x over delta x. Of course, the delta x's cancel. And so we're talking about the limit as delta x approaches 0 of 3/2. And of course, we said that the limit of a constant is just that constant. So we get 3/2. All right, so what we found was the slope of a tangent line for this particular function. Generally, when we find this, it'll be where we can plug in an x value because the slope at most of the functions that we'll be studying is going to be changing. However, this first function that we looked at is just a line, and we already know that slopes have or rather lines have a constant slope. It doesn't change, and so that's why we were able to get just this constant number 3/2. We can even look back at our slope or at our function. It's written in y equals mx plus b form, and so we see the slope here is 3/2. Well, let's try that again. In B, we actually have a parabola. And of course, we know parabolas do not have constant slopes. So how do we come up with an expression that will allow us to find the slope of a parabola, or in particular, this parabola, at various values of x? Okay, so again, we're going to start with our definition. Okay, the slope is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And so we're going to plug in, okay, limit as delta x approaches 0 of 5 minus x plus delta x squared minus 5 minus x squared all over delta x. Okay, from here, we're going to just simplify. And before we do that, let me point out, again, we were looking to express f of x plus delta x, and so I did that here. And then we also have just f of x, and that's right here. Okay? So now we get the limit as delta x approaches 0 of 5 minus, okay, I've got to square this correctly, so it's going to be minus x squared minus 2x delta x plus delta x squared. Okay, and then minus 5 plus x squared all over delta x. Okay, and if we go on and simplify, okay, we've got 5 minus x squared plus 2x delta x minus delta x squared squared minus 5 plus x squared all over delta x. Okay, and we can cancel out the 5's. We have a minus x squared and a plus x squared. And everything that's left has a factor of delta x in it. And we're going to want that. Okay, we need that so that we'll be able to cancel out our delta x in the denominator. So now we get the limit as delta x approaches 0 of 2x delta x minus delta x squared all over delta x. Or if I factor, I've got the limit as delta x approaches 0 of delta x, okay, I'm factoring delta x out, times 2x minus delta x all over delta x. The delta x's cancel each other out, so now I just need to evaluate the limit as delta x approaches 0 of 2x minus delta x. And of course I can evaluate this limit just by plugging in 0 for delta x, and when I do 2x minus 0 we get 2x. Okay, notice here that I've carried my limit notation all the way through until I was ready to plug in. Okay, once we plug in, then we can drop our limit notation, or if we find the limit in some other way, we can drop the limit notation. But we don't just carelessly discard that limit notation. We need that all the way through. Okay, also what we got here is an expression for the slope at a point. So we'll be able to talk about what the slope is at, let's say, the point when x is equal to 1 on this particular function. And then we can also find the slope when x is equal to negative 1. You know, so we use this expression to find the slope at different points. All right, so now we're going to define the derivative of a function. And it says the derivative of f at x is f prime of x. Okay, we use this notation f prime to say that this is a function that was derived or is related to the function f. So here we have f prime of x. We got it from f. All right, f prime of x is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0 exists. Then the line passing through c, f of c with slope m is the tangent line to the graph of f at the point c. Okay, when we talk about a tangent line, we're talking about a line used to estimate the slope of a function. Okay, let's say we have a function that looks like this, and I'm interested in the slope at this point. Then I'm going to draw a line that just touches the function, at least in this local area, at that point. And I use this line to estimate the slope at the point. And the way that we're able to come up with the slope of this tangent line is by using this derivative, which is, of course, the same thing as the slope formula that we were just using. So we want to find the derivative of the function by the limit process. And note here that it says by the limit process. A little bit later in the chapter, we will find some shortcuts for finding this derivative, you know, in a few seconds, just a couple of seconds. But for now, we're looking at the limit process and trying to talk about what that even means. So don't forget how to do this, but then later on, when we can use those shortcuts, we'll definitely be using them. So to find the derivative, I'm going to say f prime of x equals the limit as delta x approaches 0. This is that same expression or function we use for m, the slope, okay, is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, so we're looking at the limit as delta x approaches 0 of x plus delta x cubed minus or rather plus x plus delta x squared. Okay, all of that is just my f of x plus delta x. Is all of this, okay, because we had the cube x plus delta x. We also had to square it. Okay, now I'm going to subtract from this f of x, which is just x cubed plus x squared. And this is all over delta x. Okay, so we got to do a bit of algebra to get this multiplied out. And we can use a little tool to help us expand this very quickly. If I've got x plus delta x, I want to cube it. Okay, we are going to use Pascal's triangle. Pascal's triangle starts like this, okay? And each row always starts with a 1, and it'll end with a 1. And the numbers in between are the sum of the numbers above it. Okay, so 1 plus 1 is 2. Now, how do we use this? Okay, I'm going to use this to expand this or cube this binomial. So here we're looking at when n is equal to 2. Okay, here n was just equal to 1. All right, so let's say I have a plus b and I want to square it. Okay, then what this gives me would be the coefficients of my terms in a plus b squared. And it's this row because we're at the row where n is equal to 2. So we're going to start with 1 a squared, and then my last one is going to be 1 b squared, and in the middle we're going to have 2 a b. Okay, so notice that my coefficients here match what I have in Pascal's triangle. And notice also that for my variables, I start with 1 already at 2. In my second term, the degree goes down to 1 for the variable a. And then in this last term, the degree for the variable a is 0. All right, so we went down in degrees for a's, and now we're going to go up in degrees for b. So with the first one, it's just b to the 0. For the second one, b to the 1, and then for the last one, b to the 2. Okay. Now, this is a quick way to do this. The other way we could have simplified a plus b squared is just to say a plus b times a plus b. Okay. That wouldn't take us long because, you know, it's not a lot. But what if we had a plus b cubed, or a plus b to the 5th, or a plus b to the 100th? Well, using a method like this would be a lot faster. So if I go to the next row of the triangle, all right, I'm going to start the row with a 1. I'm going to end it with a 1. And then I get two sums, two more sums. 1 plus 2 gives me 3, and 2 plus 1 gives me 3. All right, so when I cube my binomial, I'm going to have 4 terms. All right, the coefficients on my 4 terms are going to be 1, 3, 3, and 1. Now, the way that I'm going to define or decide what my variables are going to be is I'm going to start with one variable and I'm going to decrease the powers on it. So we got 1a cubed. This is going to be 3a squared. This is going to be 3a. And then this one would be a to the 0. So I don't have to write anything. And then for my other variable b, I'm going to increase. So we start with b to the 0, then b to the first power, and b to the second power, and then b cubed. And of course, everything's going to be positive in this one. So that's how I could quickly expand a plus b cubed. Now, what's different about this versus the problem that we're working with right now is we don't have just a generic a and b. We've got x plus delta x cubed. So I can just fill it in. My a is x. My b is delta x. So x plus delta x cubed is equal to x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. All right. So that's, after the long explanation, that's the quick way for us to raise a binomial to a power. Or you could have written it out this way and multiplied the first two, the first two binomials, gotten that product, and then multiplied in this second one or this third one. Okay. But anyway, the result comes up to be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay, and that's going to be minus x cubed minus x squared all over delta x, and we still need our limit notation. Okay, so I start to cancel things out. We got x cubed, I'm sorry, our x cubes cancel out. I've got, I left something out. That was just our x cubed, x plus delta x cubed piece. We also have x plus delta x squared. So we need plus x squared plus 2x delta x plus delta x squared minus x cubed minus x squared. Okay, now we've got it all. Okay, so let's just go back and kind of look at this. What we have here is all of this. Okay, and what we have here is all of this. And then I think you can see where we have the minus x cubed and the minus x squared. Okay, all of that is over delta x. Okay, now we can cancel things out. And so I was canceling x cubed with x cubed, and then minus x squared with x squared. Okay, and notice again that everything that's left has a factor of delta x in it. Okay, we're going to need that to happen every time. So now I get the limit as delta x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x delta x plus delta x squared all over delta x. Okay. And now I'm going to factor delta x from my numerator. We've got 3x squared plus 3x delta x plus delta x squared plus 2x plus delta x all over delta x. Okay, now my delta x's cancel from the numerator to the denominator, and to evaluate everything else, we're just going to plug in 0 for delta x. Okay, and when I do, if I plug in 0 here and here and here, then I'm only left with 3x squared plus 2x. And that is our derivative. F prime of x is equal to 3x squared plus 2x. Let's try that again. We're still looking for our derivative. And so we'll start by writing out our formula for the derivative. We want to practice writing it out until we are very comfortable with it. So f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, so we've got the limit as delta x approaches 0. Okay, we've got the square root of x plus delta x minus 1 minus the square root of x minus 1 all over delta x. Okay, so we've got to evaluate this limit. And of course, from chapter 1, hopefully this looks familiar. When we saw a problem like this, we can't just plug 0 into our denominator. So what we're going to do is multiply top and bottom by the conjugate of the numerator. So we're going to multiply top and bottom by the square root of x plus delta x plus 1 plus the square root of x minus 1 all over the same thing, the square root of x plus delta x plus 1 plus the square root of x minus 1. Okay, when we do that, okay, the reason we're doing this is because we have here the conjugate pair. Okay, we've got a minus b, and we're going to be multiplying it by a plus b. And we know that that comes up to be a squared minus b squared. Okay, so it may look a little daunting to think that we've got to multiply these two numerators, but because we've used the conjugate pairs, this is just going to be the limit as delta x approaches 0 of x plus delta x minus 1. Okay, I get that because the square root times the square root, that undoes, okay, they cancel out square roots, and so we get rid of our radical, okay, minus x minus 1. Okay, the same thing. We've got here a squared minus b squared. Okay, and my denominator is going to be delta x times the square root of x plus delta x plus 1 plus the square root of x minus 1. So we go on and we simplify, and we should be able to see that when we distribute our minus sign, we're going to have minus x. So that's going to cancel with this x. And when we distribute the minus sign, we get plus 1 here. That's going to cancel with this minus 1. And so we're left with delta x in our numerator, and our denominator is delta x times the square root of x plus delta x plus 1 plus the square root of x minus 1. The delta x's will cancel, and so we get, of course, we've got a 1 here to hold its place, so we end up with the limit as delta x approaches 0 of the square root, or 1 over the square root of x plus delta x plus 1 plus the square root of x minus 1. And to evaluate this limit, I can plug in 0, and so we get this is equal to 1 over the square root of x plus 1 plus the square root of x minus 1. Okay, so I see where I made a small error, but an important error, an error nonetheless here. Okay, my conjugate should have been the square root of x plus delta x minus 1. Okay, I didn't need to change this to a plus. Okay, that can stay as a minus. Okay, and so lots of changes will follow from that. Okay, this is right. This should be minus 1, because when we square them, we would get x plus delta x minus 1. But down here, this is minus 1 as well. Okay, so that when I plug in, here we end up with minus 1 in our denominator. And so now I can simplify this to, since these are now exactly the same, square root of x minus 1 plus the square root of x minus 1, we get 1 over 2 times the square root of x minus 1. And that would be our derivative. F prime is equal to, or f prime of x is equal to 1 over 2 times the square root of x minus 1. So let's take this just a little step farther, because we don't want to just have this function that could tell us the slope at a particular point, but I want to use that function to find the slope and then go from there to find the equation of my line. So we get find an equation of the tangent line to the graph of f at the given point. Okay, so the first thing I've got to do is come up with that derivative. So we're going to say f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, or the limit as delta x approaches 0 of x plus delta x squared plus 2 times x plus delta x minus 1. Okay, that's my f of x plus delta x. And now I'm going to subtract from that x squared plus 2x minus 1 all over delta x. So we got the limit as delta x approaches 0, and we've got x squared plus 2x delta x plus delta x squared, okay, plus 2x plus 2 delta x minus 1 minus x squared minus 2x plus 1 all over delta x. Okay. And so we get the limit as delta x approaches 0 of, we've got to cancel some things out. So I've got an x squared, a minus x squared, a minus 1, a 1, a minus 2x, a plus 2x. So everything that's left has delta x in it. So we've got 2x delta x. And if you don't mind, I'm going to go on and factor out delta x. So we had 2x delta x. I factored out delta x, so we got 2x. Plus delta x squared, I can factor out delta x, so plus delta x. We had 2 delta x. If I factor off the delta x, that's just plus 2 all over delta x. The delta x's cancel, and so we get the limit as delta x approaches 0 of 2x plus delta x plus 2. And I can evaluate that limit by plugging in 0, and so we get f prime of x is equal to 2x plus 2. But that's not where I want to stop. I need to find the equation of the tangent line to this graph at the point 1, 2. So the first thing I need to find out is what is the slope at the point 1, 2. Okay, when we talk about the point 1, 2, that means we have an x coordinate of 1 and a y coordinate of 2. Okay, so I can find my slope. My slope, m, equals f prime of 1. Okay, I'm plugging in that x value. Okay, a little bit later we'll have an opportunity to plug in both the x and y. But in my derivative function, I only have a place for this x value. So we're going to say 2 times 1 plus 2. Okay, 2 times 1 plus 2 gives me 4. At the point 1, 2, on this original function f, I have a slope of 4. Now that I have a slope and I have a point, in fact, sometimes I like to write m like this. Okay, so that I know I'm looking at the slope at a particular point. Now that I have this slope and a point, I can use my slope-intercept formula, or rather my point-slope formula, to come up with the equation of the tangent line. So we get y minus 2 equals 4 times x minus 1, or y minus 2 equals 4x minus 4, y equals 4x minus 4 plus 2, or y equals 4x minus 2. Okay, so this gives me the slope of the tangent line on this graph at the point 1, 2. Okay, let me just show you what that looks like. First, I'm going to graph our function, which is x squared plus 2x minus 1. Okay. Okay, so that's our function. Now I'm also going to graph our tangent line. Okay, we found the tangent line to be 4x minus 2. So on my graph, we'll graph y equals 4x minus 2. Okay, so notice here we are at the point 1, 2. Okay, I'm going to turn off the tangent line for right now. Okay, here's our curve. We're at the point 1, 2. And what I'm trying to do is graph the tangent line, which approximates the slope at this point. So now I've put that tangent line back on, and I'm going to back out of this a little bit so we can see it. Notice how closely it comes to the point 1, 2, how well it estimates the slope of the function at that point. So we were able to come up with a function that estimated the slope at a particular point, and we've kind of drawn this tangent line in this particular case to show how well it estimates the slope at that particular point. If we wanted to look at any other point on this graph, the only thing we would have to do is use our derivative to come up with the slope at that point, and then also use the slope and that particular point to come up with the equation line. But what the derivative does is it gives us a function that will allow us to find the slope at any point. Again, our derivative was 2x plus 2. Okay, so notice if I were to put in x equals negative 1, we'd have negative 2 plus 2, or 0. When we look at our graph, notice at x equals negative 1, the slope would be 0. Okay, we would draw the tangent line horizontally here. That would be our slope, and that's going to be really important to us a little bit later. But that's how we can find the derivative, use the derivative to find the slope at a particular point, and find the equation of the tangent line at that point. Let's take a look at another example. Here again, we want to be able to find the equation of the tangent line that goes through the point 0, 3, and it's going to be tangent to this curve at that point, or f of x equals 6 over x plus 2 at the point 0, 3. So the first thing we need to do is find the derivative. So our formula for the derivative is f prime of x is equal to f of x plus delta x minus f of x all over delta x. And I forgot a very important piece. It's the limit as delta x approaches 0. Okay, and so we're going to look at this. The limit as delta x approaches 0. I'm going to plug in x plus delta x, where we have x here, so we get 6 over x plus delta x plus 2, okay, minus 6 over x plus 2 all over delta x. Okay, so here we have complex fraction or a complex fraction, and we talked about how to handle a complex fraction in chapter 1. What we're going to do is multiply the top and the bottom by the least common denominator. And we've got two denominators. They don't have anything in common, so the least common denominator is going to be x plus 2 times x plus delta x plus 2. We're going to do this on the top and on the bottom. Okay, when I do that up top, when I distribute all of this over here, the x plus delta x plus 2 is going to cancel. We're left with 6 times x plus 2. And when we distribute it here, then the x plus 2's cancel, and so we're left with minus 6 times x plus delta x plus 2. Okay, all over delta x times x plus 2 times x plus delta x plus 2. All right, so we're going to go on and simplify that a little. We've got 6x plus 12 minus 6x minus 6 delta x minus 12. Okay, all over delta x times x plus 2, x plus delta x plus 2. Okay, so we go on and cancel out. The 6x is going to cancel, the 12s, they cancel. The only thing we're left with in our numerator has a factor of delta x, and that's what we want. So we've got the limit as delta x approaches 0 of minus 6 delta x over delta x times x plus 2 times x plus delta x plus 2. Okay, the delta x's cancel out. And so we've got the limit as delta x approaches 0 of negative 6 over x plus 2 times x plus delta x plus 2. Okay, now we can go on and take the limit by plugging in 0 for delta x. And when we do, we're going to get x plus 2. If delta x is 0, then we have another x plus 2. So this gives us negative 6 over x plus 2 squared. Okay, so this is the derivative. All right, f prime of x is equal to negative 6 over x plus 2 squared. Okay, now we want to go on and find the equation of the tangent line at the point 0, 3. So the first thing I need to do is figure out what my slope is at 0, 3. So I'm going to write m 0, 3. I want to find the slope at 0, 3. Okay, to do that, I'm just going to plug in 0 into f prime. And so when I do that, we get negative 6 over 4. Because I plug in 0, we get 2. We got to square that, negative 6 over 4. Or if we want to, we can write this as minus 3/2. Okay, minus 3/2. All right, so we've got our slope. Now we're going to use our point slope formula to come up with the equation of the line. And so we get y minus y1 equals m times x minus x1, or y minus 3 equals negative 3/2 times x minus 0. All right, y minus 3 equals minus 3 halves x. Y equals minus 3 halves x plus 3. Okay, so this is the equation of the tangent line to the graph of our original function was 6 over x plus 2, and it's at the point 0, 3. Okay, let's take a look at what that looks like graphically. Okay, so here we have the graph of y equals 6 over x plus 2, and we're interested in what's happening at the point 0, 3. Notice that 0, 3 is indeed a point on this graph. Okay, and so now I'm going to draw the tangent line at this point, and we see it goes right through the point and just touches the graph at that point. And so this is a good estimate of the slope of the graph at that point.